Hello students, in this video lecturing, we will start with our fourth module, that is indexed sequential file access and prefix B+Trees. In the last module, we discussed about B-Trees. Here we will discuss about B+Trees. Okay. Indexed sequential access. What is indexed sequential access? Until now, whatever methods we have discussed was either we have viewed the file from indexed point of view or from a sequential point of view, right? Okay, but here the indexed sequential access is not a single access method, but rather it combines both, that is the sequential access to records ordered by key and indexed access to those same record. Okay. B plus trees, which we are going to discuss here, is just one method for providing the indexed sequential access. Okay. An example where we can use this indexed sequential access is our student record systems at universities. That is, they require a keyed access to the individual records, while also requires the large amount of batch processing. Okay, that is the simple example in our day-to-day. Okay, next is maintaining a sequence set by the use of blocks. Okay, a sequence set is a set of records in physical order, which is such that it stays ordered even if the records are added or deleted. Okay, this sorting and resorting in order to keep the sequence set maintained in a order is very expensive. So what we can do is we have to look into a way to localize the changes. The idea is to use blocks that can be read into memory and rearrange there quickly. Like in B-Trees, even blocks can be split, merged, or other record redistributed as necessary. Okay, all the operations performed on B-Trees can be performed on this particular blocks also. However, there are certain costs associated with this approach. Those are the internal fragmentation cost and the cost for physically ordering the blocks. Okay. Following diagram shows the block splitting and concatenation due to insertions and deletions in the sequences set. Okay. Now see to figure A, which shows the initial blocked sequence set. Okay, it shows three blocks, that is block 1, block 2, block 3 in order. The link from block 1 to block 2 and block 2 to block 3 shows the order of sequence set. Okay, now assume that the order of each block is 4. That is, in each block you can have only 4 records. Okay, now see to the figure B, which shows the insertion of a key, that is character, which is to be inserted into block 2 there. Okay, see to figure A there to understand the insertion. Okay, the key character which starts with the C, which is to be added, needs to be inserted between Carson and Cole. But the order of block 2 is full. So we need to split the block into 2. one block, how to split, we can fill one block with the 3 records and another block with the 2 records. In block 2 itself, you will maintain the initial 3 records including character, and the other 2 records are placed in block 4. After placing, we have to change the link and connect block 2 to block 4 and block 4 to block 3 in order to maintain sequence set there. Okay. Now see to the third figure C there. Okay, it shows the sequence set after deletion of Davis record from figure B. When you delete Davis from block 4, there is an underflow. That is, you are left with only one record, that is coal. So you have to merge block 3 and block 4 there. Okay. 2 records from block 3 are appended to block 4, and block 3 is empty now and can be reused. So next what you have to do, you have to change the link from block 4 to block 3 is removed now. Okay, so the link what you have is block 1 to block 2 and block 2 to block 4, and now the block 4 is available for reuse there. Okay. Next is the choice of a block size. With our sequence set, a block is the basic unit for our input output operations, right? So when we read data from the disk, we usually read at least one block from the disk, and similar way, when we write the data to the disk, we write at least the minimum one block. So the size of the blocks needs to be considered. There are 2 considerations to keep in mind when choosing a block size. The first consideration is that the block size should be such that we can hold several blocks in memory at once. Okay. The second consideration is that the block size should be such that we can access a block without having to bear the cost of a disk seek within the block read or block write operation. Next is adding a simple index to sequence set. In the sequence set which we discussed, the blocks contains a range of records that might contain the record we are seeking, as shown in the figure. Okay. For this sequence set, we can construct a simple single level index called complete indexed sequential access. This is good only if the entire index can be held in memory. Otherwise, instead of a simple index, we can use B-tree index, okay, which we will discuss next. After the simple index, we will discuss how to use the B-tree index. Okay. The table in the figure shows a simple index for the sequence set blocks. It shows the key and the block number. The table shows the key for the last record in each block there. Okay. Since this is a simple index, we used names or keys in the index. Okay. But because we have to consider the memory, we have to think about utilizing less memory for key storage, isn't it? So what can we use? Now we have to think about the content of the index, how we can reduce the content of the index, whether it is possible to reduce the content of the index. Okay. The content of the index, separators instead of keys. We can use something called separators instead of keys to separate the blocks, or say distinguish between the blocks. These separators occupy less space than keys. The figure shows one possible set of separators for the sequence set and the rules to identify the keys or records in the blocks. See the rule says that if first rule says if the key is less than the separator, then the record is present in the left block. That is, record is found in to the left of the separator. Else, if the key is greater than or equal to, that is the second and the third rule. Okay, greater than or equal to the separator, you have to search to the right of the separator, to the right block. You have to search for the key. Okay. For example, if you want to search for the record Davis, then the key Davis is less than the separator E there, isn't it? So record will be present in the third block. You can search for the third block for the key Davis. Next is the simple prefix B+Tree. The separators we just identified can be okay. Simple prefix B+Tree. B tree index is called the index set. Okay. I told you this separators we just identified can be formed into a B tree index of the sequence set blocks, and these B tree index is called index set. Okay. Now the B tree index plus the sequence set blocks together forms the simple prefix B+Tree. When we say simple, it means that it indicates the shortest separator. That is, we have to use the shortest separators possible. Then only you can have less memory compared to the actual key storage in the index. Okay. And one more thing is the B tree index plus the sequence set blocks together forms the simple prefix B+Tree. Okay. Next is this figure shows simple prefix B+Tree. Here you can see the B tree index built up on sequence set blocks. That is, which is the sequence set blocks there. Block 1, 2, 3, 4, 5, 6. These are called the sequence set blocks. Okay. And index, what are the indexes there? One node with the E and the block with the separators BO and CAM, and one more right node with the separators F and forks. Okay. So these are the sequence set and index set. This together forms the simple prefix B+Tree. And you can see that the records are stored at the leaf there. Okay. In the blocks, you have to search for the blocks to find the records. Okay. Simple prefix B+Tree maintenance. How to maintain the simple prefix B+Tree? Like the maintenance for the B trees, you have the maintenance for a simple prefix B+Tree also. First thing to be considered is changes localized to single blocks in the sequence set. That is, when you have to change a single block in a tree, what, where and all you have to reflect the change. That is nothing but see to this diagram here, which shows the changes localized to single blocks in the sequence set. Whenever you change a single block, usually you have to alter the block plus the index of the block, that is the parent node also. Okay, that is how you do with the single blocks. Okay, here is an example given: deletion of Emery and Folks records from the sequence set leaves the index set unchanged. And that is see to the previous example here. See, from this B plus simple prefix B plus tree, you have to, when you delete Emery, where is Emery? That is the fourth block. Okay, if we remove Emery from there, there is no change. Just you can just remove, that is, do make the changes to the fourth block only. Okay, and one more is folks is present at the block 6 there. If you want to remove, just do the changes to this particular block 6 only. Okay, you need not make any changes to the index set there. Okay, that is what the result is after changing the Emery and Folks. Now the second one, that is changes involving multiple blocks in the sequence set. That is when you change more than one block in the sequence set, what maintenance you have to do. An example is given here: insertion into block 1 causes a split and consequent addition of block 7. See to this diagram here. In case if block 1 is full and you are trying to insert one more new record, in that case you have to split this first block into 2. Now you have blocks until 6. So the second, after splitting the first block, you have to add block 7. Understood? You have to add block 7 there. Okay. When you add one more block there, that is after one, when you add one more block there, what happens is you have to add one more separator to the index set. See, now the separator to be added is AY. But see, in the previous diagram, you already have two separators there, isn't it? That is a BO and CAM. Now you want to add one more separator, that is AY, resulting from the split. When you want to add AY to this BO and CM separator, what happens is that particular index node will overflow. Okay. When you have an overflow, what you have to do? That particular index node, you have to split it. Okay. That is what you have done here. You have split this AY, BO and CAM. You have to split it into two nodes. One is with the AY separator and one more is with the CAM separator, and the middle separator will go to the root node there. So in the root node, earlier you had only one separator, that was E, but now you have added one more separator, that is BO. Okay, that is what you are doing when you insert and perform, how the split is done and the changes required to do. Next is one more example is given here. Deletion from block 2 causes underflow and consequent merging of blocks 2 and 3. See to the previous diagram to understand this. You want to delete some records from block 2 and block 2, right? Yeah, block 2. And what happens is it will result in underflow. Underflow means, see, always there should be a minimum count of records in the block, otherwise it is not valid. So when this underflow occurs, so you have to merge the blocks, possible blocks. Here you can merge block 2 and block 3. That is how you maintain the merging. Okay. After merging, block 3 is no longer needed and can be, that is, you are going to copy all the contents from block 3 to block 2 and block 3 is no more needed. So can be placed on an avail list. With what is this avail list? We had discussed in the second module. Avail list is nothing but those nodes which are deleted. Okay, and the space is available for insertion of new keys there. Okay, such are called avail list. You have a list of deleted spaces. Okay, you are going to add this block 3 to that particular avail list there. Separator CAM is no longer needed. Okay, so removing CAM from its node in the index set, that is in the second level. Okay, index set forces a merging of index set nodes. That is from the previous diagram. You can say AY and CAM was there. You can merge these two together now. Okay, merging of index set nodes, bringing BO back down from the root. Again, in the root, you have only one separator there. Next is index set block size. That is what block size you have to select for the index set, whether you have to select the same block size or different block size than the sequence set. The answer is always it is better to select the same block size as the sequence set block size. The reason, there are two reasons for that. First one is usually we select the block size for the sequence set based on the factors like the characteristics of the disk drive and the amount of memory available. Same factors we will consider for this index set also. Therefore, the block size that is best for the sequence set is usually best for the index set as well. Okay. Next is see, usually this index set blocks and the sequence set blocks, we store it in a same file to avoid seeking between two separate files. If you store the index set block and sequence set block separately in separate files, you have to seek twice to access. Otherwise, if it is in the same file, then you can have just one access. Okay. Now for accessing, usually we will prefer a simple prefix B+Tree. When we prefer this simple prefix B+Tree, it is always good to go for the same size for both, that is for the index size as well as for the sequence set. The size of the blocks should be the same. Okay. Next is the internal structure of index set blocks, a variable order B tree. The internal structure means inside the index set block, how the separator and the RRN and or the this one, that is what you can combine the separators and index to separators and the list of RRNs, how you are going to club into the index set block. Okay. Given a large fixed size block for the index set, how do we store the separators within it? With the large size of index set block, how to store the separators with it? There are different ways to combine the list of separators, index to separators, and the list of relative block numbers, RBNs, into a single index set block. One possible approach is which includes a separator count and keeps a count of the total length of separators. Okay. This figure shows the same approach here. Okay. Before that, let's see what is separators and index to separator, how it is given. See here, you have concatenated separators, all the separators combined together into one space, followed by the index to separator. These indexes are nothing but it reflects the position of the this separators. Okay. See, to the index to separators, your first index to separator is 0 0. That is the first separator starts at position 0. That is A. Okay. Next index to separator is 2. That is the second separator starts at position 0 2 there. That is B. A. Third one is at position 0 4 there, where is 0 4, that is B R O. How did you select three alphabets there? Because the next position is 0 7. When that is 0 7, you have capital C there. So until 0 7, it is the third separator. Okay. Again, you have the next separator C, followed by CH, followed by CRA, followed by the separator DELE, all this, and you have the index to all the separators. Okay. Now see to the first approach there, where initially you will have the separator count, that is in each block there, A, B, A. How many separators are combined there? How many? It is 11. Okay. Followed by total length of separators, nothing but the alphabets. If you count the alphabets, you can get the total length of separators, that is 28 there. Okay, followed by the combined this one, that is the separators, followed by the index to separators, and followed by the relative block numbers, that is first separator, where in which block, that is it refers to block 0 0, and the second one refers to the block 0 1, and so on. One more approach is placing the separator between the blocks. See to the figure here. Here you have B00, that means block 0. Between block 0 and block 01, you have the separator AS. Index to AS is 0, or you can say separator subscript is 0 there. The second separator, that is a BA, it is placed between block 01 and block 2, and the index to the second separator is 1. Similar way, you have the third separator, that is B02, B03, that is between block 2 and block 3, you have the separator BRO, and the index to this separator is 2, and so on. This is one more approach for placing the separators and block numbers in the index set block. Okay. Next topic is loading a simple prefix B plus tree. This topic we will discuss in the next session. So, thank you students for listening. Hope you all understood.